So we start with the same commutation relations, and obviously we get the same things, except that we now have this S operators. Okay, we make this distinction between S and L because a time will come when we have a particle which has both orbital angular momentum and spin angular momentum. Okay, so we'll have to see how these things add up and such things. Okay, so we just go through the same process. We say that based on those commutation relations, I can construct a total spin, okay, operator, which is going to be Sx squared plus Sy squared plus Sz squared. And all of these components commute with it. So S squared Sy is equal to 0. S squared Sz is equal to 0. So that means I can just pick up one of them, say Sz, and construct eigenkets, which are eigenkets of both Sc and S squared. So what do I have? I have this S squared, okay, S ms. Okay, so this is like Lm, except that now I call them S and ms. So this is going to be, excuse me, S bar squared S plus 1, excuse me, S ms, and Lz S ms is equal to H bar ms S ms. I still have my raising and lowering operators, L plus, no, S plus now. S plus is equal to Sx plus I Sy, and S minus is Sx minus I Sy. How do these things work out? Well, S plus on S ms does not change S, so S is the same, but ms goes by 1. Okay, and the proportionality constant is again S plus 1 minus ms plus 1. Okay, and there's an H bar which I can squeeze here.
So the
Yes.
This would be Sc.
Hmm?
The Lz without S squared.
And the
Without
left
S squared.
part of the board.
No, no.
No, the left bottom.
That one.
Yes.
There's
Okay.
Lz. This would be S squared.
Yes, okay, thank you. Okay, and for the S minus, I have S ms. If I hit on it with S minus, I'm going to get, okay, a similar factor, S plus 1 minus ms minus 1 H bar S ms minus 1. So exactly the same things, except that we have S in place of L. And the structure is, we start with a state S and go down with each application of S minus to one lower level, etc., until I reach minus S. And again, this allows me, when I'm going down by one step at a time, like this, I can either have S equal to 0, 1, 2, 3, etc., or S equal to 1 over 2, 3 over 2, 5 over 2, etc. Okay? So these things, again, so I'm just repeating what I wrote over here, but these things are bosons, and these things are fermions. Okay? All right, so now that we have done this, what I'll do is I'll just concentrate on the spin 1/2 case. because it's probably the most important case that we'll have, because that corresponds to the electron. So the spin 1/2 case. Okay, spin 1/2 means S is equal to 1/2. So ms can be plus or minus 1/2. So there are two possibilities. So ms is either up or down. Remember, that's the z component of the angular momentum. Okay, so it is, you see now, this is a very small Hilbert space. It's a two-dimensional Hilbert space. There are only two possibilities. So I have the possibility of, okay, so two, okay, states corresponding to SZ measurement. So what does that mean? Here comes my electron. Okay. Now, to represent spin states, we usually use this letter chi. Okay. It's not X or something. Okay. While you are learning these things, you should also develop your handwriting in the Greek alphabet. Okay. When reading exams, I'm terrified with these notations, whether it's a Q or a sigma, or it says you don't use these things interchangeably, right? This is chi. Just work on it a little bit. Okay, so here comes our arbitrary spin state. And this is my measurement, SZ. And there are two possibilities, okay? It is either 1/2, right? That means, what does that mean? That means LZ operating on this. So let me just even write it down. So L squared on 1/2 is equal to h bar squared, okay, 1/2 plus 1 times 1/2, right?
So is it an S square? Not L square?
Yes, S squared, thank you. I'll make this mistake a lot. So this is the total angular momentum. So you get, okay, so you see, after a point it becomes tiring to write 1/2. So there's a nice shorter rotation notation. I say this is S squared upspin. I don't know if it's easier to write, but it's an arrow pointing up. Okay, so this means 1/2, okay, is equal to 3/4 h bar squared upspin. Okay, so this is also upspin. If I don't specify anything, it's upspin in the z direction. Okay, so it's the result of a measurement in the z direction. Then other possibility is equal to S part, again the same, minus 1/2. So that's, we are going to call that a downspin. Okay, so I can play the same game here. So S squared downspin is going to be the same S, so I'm going to get the same thing, 3/4 h bar squared downspin. But if I look at SZ, for example, downspin, then it's going to be minus h bar over 2 downspin, right? Okay, so those are the properties, yes.
When we are measuring,
Okay, well, we'll see that, okay? We'll see how to add these things up, okay? We'll have to look at the total angular momentum in general, okay? So we'll look at the total angular momentum, but at this point, you see, when you are measuring the spin of some object, okay, you generally have arranged things so that in your experiment, In fact, I'll put a link in the course web page for a nice experiment, desktop experiment, which measures spin angular momentum. You arrange things so that the orbital angular momentum is 0. Okay, so this thing usually, what you do is, since the electron itself has a charge, it's in some ways it's easier, some ways more difficult to isolate the effect of the charge. So you try to use neutral objects. So a neutral object is something, for example, like an atom, a silver atom perhaps, where you have more than one particle, obviously, but their angular momenta add up in such a way, so there's a closed shell, chemical shell, which everything adds up to 0 angular momentum, but then there's a nice one single lonely electron. So you measure the angular momentum of that remaining part. Okay, but at least in principle, what you do is you take this particle. Okay, so this experiment is called a Stern-Gerlach experiment. And what you do is you have a particle coming in and it has a magnetic moment. Okay, so spin is associated with with magnetic moment. Okay, so it's like a rotating charge. Because it has a spin, it has a magnetic moment. If it's a negative particle, magnetic moment is in opposite direction to the spin. And this magnetic moment now you can influence by applying a non-uniform field. So if you have a non-uniform field, a field which is growing in one direction, okay, if the field is non-uniform, you see the force acting on the dipole at this end compared to that end is stronger, so there's a net force on the object, so it pulls the particle in one direction or the other. Okay, so you have the electron beam coming in, and you just have a deflection here in the path of the particle proportional to its magnetic moment. And in fact, it was quite exciting to find out in the initial experiments that there are only 2 possible values for the magnetic moment or the spin. Yes?
So magnetic moment is only associated with spin, not orbital angular momentum at all.
No, orbital angular momentum will also have but you have to design your experiment. Okay, so if experimental work is difficult and challenging, so you have to set up your system so that the orbital angular momenta, for example, cancel for all particles. Okay, so the total angular momentum associated with all of the particles is equal to 0. In fact, the total spin angular momentum for almost all of the particles also add up to 0, and you have just an additional electron on which you are measuring things. Okay. Okay, so I'll put a link to the Stern-Gerlach experiment because it involves a lot of technique, and it's interesting to see how people do such things. Okay, so it's a good thing. Okay, so but in principle, you see, nowadays you can do this experiment with a tabletop experimental setup and find out that you get these 2 paths, okay, corresponding to an upspin and a downspin, and nothing in between. So the angular momentum, spin angular momentum, is quantized, so it's very clearly shows up. Okay, other questions? All right, let's go on. Now, I want to do a little bit more than this. I want to put this now into an SX experiment and perhaps an SY experiment and such things. So I want to now find out how those operators are constructed. All right, let's see. So, let's look at all these operators. SZ, let's start with SZ, SX, SY operators in the, okay, up, down basis. So I'll generate matrix elements associated with these things. Okay, so SZ is obviously the simplest one. Okay, so I take SZ, it's going to be a 2 by 2 matrix. It's just a two-dimensional Hilbert space. On the right-hand side, I have upspin or downspin. On the left, I have upspin or downspin. Now, this is SZ in its own basis. Diagonal. So it will be diagonal. So I'm going to get up expectation value of SZ, which is going to be h bar over 2. Down expectation minus h bar over 2, 0, 0. Okay? Now to find Sx and Sy, again, it is easier to use the S plus and S minus operators. Okay, so what does S plus operator look like? So I have up, down, up, down, and S plus between them. So S plus raises whatever it has on its right. So the only element that will be finite is going to be this one, right? So it will raise this down spin to an up spin. This one, it cannot be raised anymore. Okay, so this one will have no inner product. So these things will be 0. And this thing is what? Square root of S plus 1 minus ms ms plus 1, right? So what is it? 1 over...
Square root of 3 over 4 minus 3 over 4.
Okay, just tell me the result. 3 over 4, okay, minus 1 over 2.
Minus 1 over 2.
And this is, let's see. This is the lower one, right? So it's going to minus a half. So it's going to be minus 1 half, minus 1 half plus 1. So this is
And
what?
S plus 1 should be 3 over 4, but 3 over 2.
3 over 2, thank you. Okay, so this is 3 over 4 minus.
Minus 1 over 4.
So this is
Plus 1 over 4.
which one? So this is plus, okay, plus 1 over 4. Okay, so it's going to be 1, right? So after all this struggle, we get just 1 h bar. Okay. So what about S minus? Same sort of thing. Up, down. Okay.
It's
Up.
just that joint operator, so 0, 0, h bar. 0.
Yes. Okay. That's a good way to do it. It's the adjoint. So we should get h bar 0. Okay. And that means I can now find what Sx and Sy are. Sx is going to be equal to 1 over 2 S plus plus S minus. So it's going to be h bar over 2, 0, 1, 1, 0. Okay, Sy is 1 over 2I, because now I have to cancel the I as well, wherever it is. Okay, S plus minus S minus. So I subtract this from that and divide by 2. So I'll again get h bar over 2, but I'll also have a 1 over I, which is going to go into as 0 minus I 0, right? Okay, so we determined all of these objects. Now, there is a customary way of writing these things. For example, Z, we write it as h bar over 2 times the matrix sigma Z, okay, which is just going to be a simpler matrix. Sx is going to be h bar over 2 sigma x. Sy is going to be h bar over 2 sigma y. Okay? Yes?
Sigmas represent matrices, right?
Yes. In fact, let's write them down. So sigma z is 1, 0, 0, minus 1. Sigma x is 0, 1, 1, 0. And sigma y is equal to, okay, 0 minus I 0. Okay? These things are called the Pauli spin matrices. So you see in the early days of quantum mechanics, the who is who in quantum mechanics had their names associated with all of these stuff. Okay, so you see that these things have very nice properties. For example, if you take any one of them, let's call it sigma I, if you square it, you are going to get an identity matrix. Okay, that means the eigenvalues are, okay, it's consistent with the fact that the eigenvalues must be +1 and -1, right? Because all of these things are now spin matrices. So we are going to look for its eigenvalues. And as eigenvalues, we expect to get plus or minus h bar over 2. So the matrix part of this thing should have eigenvalue plus or minus 1. It's quite explicit in the sigma z case, but you can just verify that all of these matrices have plus or minus 1 eigenvalues. Okay. You can also see that, let me see, if you look at sigma I, sigma j in cyclic U, so if this is sigma x, sigma y, this is going to be equal to I, bad notation, not this I, this is square root of -1, and sigma k. Okay, so they form a nice cyclic relationship among themselves.
They also form a basis of all two-dimensional Hermitian matrices.
Along with a unitary matrix. Okay, so if you add, so what your friend is saying, that take any arbitrary matrix A, B, C, D, you can expand it in terms of these things plus an identity matrix. Okay, sort of makes sense. You have 4 independent variables and 4 matrices will be sufficient.
Not for all matrices, but Hermitian matrices.
Okay. I'm not sure about the Hermitian part. Yes, it has to be. Okay. Okay. Any questions? Oh, we have lots of time. Okay. So now I can make more complicated experiments. So, but to make more complicated experiments, I need to find the eigenvectors of Sx and Sy. Okay. So let's look at eigenvalues and eigenvectors of Sx. Okay, that's relatively simple. I'll perhaps leave Sy out, maybe not. Okay, so let's see. First of all, it's really quite clear that I have this sigma x minus I times lambda is going to be equal to 1 minus 1 lambda. Okay, so I'll work with the sigma matrices. The S matrices will just have h bar over 2 multiplied with them. Okay, and if I now look at the determinant of this, so that I have that, I have lambda squared minus 1 equal to 0, and lambda equals plus or minus 1. So eigenvalues of sigma x is plus or minus 1, which means that eigenvalue of Sx is going to be plus or minus h bar over 2. So it doesn't matter which direction you measure the spin in. Okay, nature doesn't care which direction you call x or y or z. You make a measurement, you are going to get plus or minus h bar over 2 as the result of the measurement. What are the eigenvectors? Okay, so I have this structure 0, 1, 1, 0. Okay, so that's our sigma x. You can very easily see that something like 1, 1, okay, so you don't have to calculate the eigenvectors each time you see these matrices. After a while, when you do this 132 times, it becomes sort of a reflex. You see, if you multiply this by that, you get the same vector, right? So this corresponds to lambda equals 1. I want to normalize it, so it's 1 over square root of 2. Now, I want also the eigenvector which corresponds to lambda equals minus 1. What will that look like? Can you tell that just by inspection?
Minus 1. I'm sorry.
It has to be orthogonal to this one, by the way. Okay, 1 minus 1, right? So 1 minus 1, again 1 over square root of 2. You see this is lambda equals minus 1. If you just multiply this vector with that, you see that you get minus 1, 1, okay, because this interchanges the two rows, and that's my eigenstate. So what does it mean in terms of the states? Well, this state corresponds to an upspin in the x direction. Okay, so we use this notation for it. This corresponds to an upspin plus h bar over 2 eigenvalue for upspin in the x direction. Okay, and this one corresponds to downspin in the x direction. So upspin in the x direction is equal to, well, maybe we should have, of course, discussed the sigma z case also, but the sigma z case is so simple. Let me just write it over here. Okay, so the up z, okay, is just corresponds to 1, 0, and down z corresponds to 0, 1, right? Remember, because sigma z, okay, is equal to 1, 0, 0, minus 1, right? So this just picks up the first eigenvalue. This one picks up second eigenvalue. Okay, so you see this up x is made up of up z and down z. Yes?
Also, it might be a silly question, but why we call eigenvector of lambda 1 as a up and other as a down?
Okay. No, it's a very good question. Okay, so we are making a measurement of Sx, right? Now, Sx has two possible outcomes, h bar over 2 and minus h bar over 2. Okay? So this over here is up x. This one here is down x. Okay? The one which corresponds to eigenvalue plus h bar over 2, okay, is considered the up x. It's up in the x direction. And this minus h bar over 2, okay, is that. So when we look at sigma x without h bar over 2, we get eigenvalues plus or minus 1. Okay, so sigma x is equal to, if I try to expand it in terms of sigma z, what would I get? How do I expand this 1, 1 in terms of 1, 0 and 0, 1?
By using the identity element.
Well, okay, but just by inspection. Can you tell me how much 1, 0 there is in this and 0, 1 in that?
Square root of 2.
Okay, 1 over square root of 2.
One of them.
Okay, up z. Well, I don't have to write the z. It's just up. If I don't write the z, it's understood to be in the z direction. 1 over root 2 down, right? So 1 over root 2 this plus 1 over root 2 that gives me up x. Similarly, down x is equal to what? Okay, 1 over root 2 up z minus 1 over root 2 down z. All right, so now let's develop our experiment one more step. Okay, so what I'll do is I'll first do the x experiment. Okay, so let's take this general spin vector. Let's do an x measurement. Here comes plus h bar over 2. Here comes minus h bar over 2. Okay. So now let me choose one of these things. Let me choose this minus h bar over 2 part. So this now is in the state of down x. Now I want to measure SZ on it. Okay. So what are the possibilities? Possibilities are always the same. Okay, it's either plus h bar over 2 or minus h bar over 2. But what are the probabilities? Okay, it's the magnitude squared of these things, so it's down. So it's the square of this and square of that. Okay, so I'm going to get probability 1/2 for this, probability 1/2 for that. Okay, 50-50. Now, suppose I measure Sx again. What do I get? One for the probabilities.
And we should first expand the,
Okay, but what do you expect?
I'll say, 1 over 2.
Okay, very good. 1 over 2, 1 over 2 is the correct answer. But let me tell you an interesting statistics. I ask a problem like this in every exam over the last few years. And there are always people who say, well, we measured it once, so it has to minus h bar over 2. That's not how it works, right? These are incompatible measurements. Measuring SZ will destroy the measurement on Sx. Okay, so technically, yes, we have to now expand this Sz, okay, which is going to be up z in terms of up x and down x. Okay, so we have to find these coefficients. But it's not really that difficult, right? Because how do I combine this up x and down x to find, for example, up z? If I just add them up, right, these lower terms are going to cancel, but I have to keep the normalization. So I'm going to just keep getting 1 over root 2, 1 over root 2. So the measurements here are h bar over 2 and h bar over 2 with probability equal to 1/2 and probability equal to 1/2. Okay? So this is very nice. It just shows you how these things work out. Okay, let's, just to be fair, let's do the SY also. Yes, we have time. All right, so let's look at SY. Okay, so SY is equal to h bar over 2 times this sigma matrix, which is 0 minus I 0. You can again see very simply that you are going to get a lambda squared minus 1 equal to 0 for the characteristic equation. So lambda equal to plus or minus 1 for this matrix part. Obviously, with h bar over 2, it was going to be plus or minus h bar over 2. But let's just look at the eigenvectors. So I have this 0 minus I 0, nice Hermitian matrix, multiplied by something which is going to give me 1. Okay, let's look at that eigenvalue first, times the same thing. So what is that? Okay, the way I like to do it again, if I'm not sure, is I put 1 and a here, 1 and a there. Okay, so this gives me what? Minus IA is equal to 1, or a is equal to I, right? So this corresponds to lambda equal to 1, which means that the eigenvector is 1 and I. And if I want to normalize it, what do? 1 over square root of 2, right? Okay, so that's the lambda equal to 1 case. The lambda equal to minus 1 case is 0 minus I 0. Okay, 1 and a is equal to minus 1 and a. Okay, so this is the lambda equal to minus 1 case. So this time the first equation gives me minus I times a is equal to minus 1. Okay, so a is equal to minus I. Okay, so that eigenvector is 1 minus I, 1 over root 2. Okay, just to make sure, you can just find the inner product of these two and check that it is equal to 0. Is the inner product equal to 0?
Yes, they should.
They should be, of course. Are they?
Yes, nice stats.
Mm-hmm.
Yeah, nice stats.
Careful.
No, they should. They are. They are definitely orthogonal.
Yes, if you believe in mathematics, they should be. But can you do the algebra?
1 plus square root of I minus.
Okay, you shouldn't forget to take the Hermitian adjoint, right? So this is 1 over root 2, 1 minus I, okay? 1 minus I. So now you see this is 0, okay? So just don't multiply them together, okay? They are not real, okay? All right, so you see now I can construct these things also out of the up z and down z. So this corresponds to, over here, an up y object. Okay, an up y object is equal to 1 over root 2 up z plus I over root 2, okay, down z. Okay, I'll just drop the z's. So that's what up y is. And down y is 1 over root 2 up x minus I over root 2. I'm sorry, this is just z down z. So you see, again, these things all correspond to probabilities 1/2 and 1/2. So no matter which way you go, when you make an SX measurement and then a measurement which is perpendicular to it, you have 50-50 probability of getting up or down. Okay, so this is quite basic. It doesn't matter if you measure the y component here, x component there, as long as they are perpendicular to one another, okay, you get 50-50. Now, what happens if the directions are not perpendicular? Okay, so in that case, okay, no, we don't just make quick theories like that. Okay, we have to do calculations, right? So, well, we have to find the operator which corresponds to that measurement. Okay, so suppose I have this, again, beam coming in, and here I make a measurement, say, in some direction. So let me denote it by that. S in the direction of a unit vector. Okay, no direction, no matter which direction I measure, I'm going to get, I have these two probabilities, h bar over 2 and minus h bar over 2. Okay, now suppose I take this beam, which corresponds to, okay, up, but in the n direction. Now I perhaps measure it in the z direction. Obviously, the result will depend on the relationship between n and z, right? N could be the z direction, perhaps. Then we know what happens. N could be the y direction, etc. So we have to specify what n is and make our calculations according to that. So how do I define the n direction? Well, I have these x, y, and z directions, right? And n is some general unit vector, which goes like that. So it's going to have x, y, and z components, right? So it's going to have a z component, an x component, and a y component. And it will depend on these angles. Okay, so I have this theta and phi. So theta and phi define the direction of this unit vector. So I can write this down very easily. N is something in the z direction, proportional to cosine theta, something in the x direction, which will be sine theta cosine phi, plus something in the y direction, sine theta sine phi, right? So this Sn is going to be n dot product with the general S vector. What is the general S vector? It is x Sx plus y Sy plus z Sc. Okay, so I find the dot product, which gives me some combination of xx, si, sz. So now I have to collect them together and construct the matrix. Okay, and I'm afraid we cannot probably finish this by that time. Yes. Okay, so I'll leave you with this exciting thought, which we'll finish on Monday to find out. Yes.